All right, here's something that we kind of skipped over, and now we're going to come back around to it. The derivative of inverse trig functions. So I'm doing this a little differently than most people will do it online. I mean, in the end, it's all the same stuff, the same mechanics, but I'm going to relate it back actually to a lot of people do it through implicit differentiation. So if you want to see another way to do it, you can check pretty much any other video online. I would just recommend probably Khan Academy. He does a good job with all his stuff. I'm going to look at doing it with the formula for an inverse that we've learned already. So if we want to find the derivative of any function's inverse, we use the formula 1 over f prime of f inverse of x. All right, so we're going to use that to develop the derivative of inverse sine. So using that, I'll write it again down here. Using this guy, our equation for finding the derivative of the inverse, we're going to say that the derivative of the inverse of sine is going to be equal to 1 over f prime. So if f is sine, then f prime is cosine of x. And then, of course, f inverse of sine, well, I don't want to put that there. That might confuse us a little bit. So f prime is cosine, and then inside of the cosine, I don't put x, I plug in the inverse of sine of x. All right, and so now when we compute this thing, we'll have the derivative of the inverse of sine. So what we need now is a little drawing. Remember that inverse trig functions, right, or any inverse function, we switch the domain and the range. Okay, that's the big idea there. So typically, a trig function, its domain, if I think of that function machine, right, its domain is an angle. We usually plug in some kind of, we call it theta in general. We plug in an angle, and its range or its output is, I'll just call it a trig value. It's kind of geometrically, it's a value of whatever. It's just a value, a number, okay? So I'll say that it spits out a trig value. Some examples of these that you might recall is like sine of pi over 3 is going to be equal to root 3 over 2. Right, so there's our angle for our input, there's our trig value for our output. All right, so just to give you a reminder of what that is. So now the inverse trig functions, those take trig values as input, right, like say root 2 over 2, and they spit out angles. So we'll say, it spits out an angle. All right. So an example of that is if I do, like I said, inverse sine of root 2 over 2, we're going to get pi over 4. So there's our input of the trig value, and it actually returns an angle. So an inverse trig function, the answer is going to be an angle. And also we have to kind of remember that that angle is, we have some domain, or I should say range restrictions to keep it as a function. So what that means for us here is, we're not concerned with what angle is the inverse sine of x. We're just concerned with, we know there is some angle. There is some angle here that equals that inverse sine. It spits out the answer of an angle, okay? So that means I can draw a triangle, a right triangle, and I'll put that angle, theta. I can put it there. I can put it in the other angle if I want. There's some trig value or trig ratio, right? These trig values are ratios. So maybe that's the word I should have used over here, is trig ratio instead of trig value, but okay. I think of it as x over 1. So there's some angle whose sine value is x over 1. How do I know it's those sides? Because sine is opposite over hypotenuse, right? So now I don't really care what that angle is. I don't care what the measure of theta is, because now I just want to find the cosine ratio of that angle anyway, which is going to be 1 over the cosine of that angle is going to be adjacent over hypotenuse. So it's going to be 1 over, well, I've got to find adjacent here. So if I do Pythagorean theorem, I get question mark is equal to the square root of 1 minus x squared. Square root of that, right? I kind of skipped a bunch of steps. but that is what our cosine of theta is equal to. So that is the derivative of our inverse trig, of our inverse sine. So I'm going to say that, well, I'll write it down here. No, not yet. Sorry. Oh boy, disaster. So we're going to say that's equal to our derivative of the inverse of sine of x. Some things to note. There is no sine or cosine in there. It's just that kind of equation there. So you can work through this if you like all the time, or we can start to remember this. And if you think of this triangle and this ratio, this as being x over 1, you can kind of work through quickly in your head that that's the square root of 1 minus x squared, and that'll kind of help you remember what these formulas are. All right, so now we're going to do something similar for cosine of x. So again, f prime of x, we're going to need that, we know, right? So this is negative sine x in this case. So now I know the derivative of the inverse of this guy is going to be 1 over f prime of f inverse of x. So again, I'm going to make my substitutions here. 1 over f prime is really negative sine of inverse cosine of x. So that means there is some right triangle, there's some angle in a theta in a right triangle somewhere where the inverse cosine, that angle theta, has an inverse cosine value of x, which means x over 1. So adjacent over hypotenuse. And then by a similar Pythagorean theorem, I would find that that side, again, is the square root of 1 minus x squared. So this angle theta would replace all of this, because that's the output for that inverse trig. I just get the angle theta. And now I want to find the sine of that theta, which is opposite over hypotenuse. So now I have, I'm going to put my negative up top. So I have negative 1 over, and then my sine function is going to be opposite over hypotenuse. So it's this over 1. So there is our inverse, the derivative of our inverse cosine. I used a different notation here on purpose. Remember that arc sine or this negative 1 notation can both mean inverse trig function. Also, sticking to some of our derivative patterns that we've noticed, the derivative of a cofunction is negative. This is not a cofunction, that's why its derivative is positive, or not why, but that's a pattern we're noticing. Okay? Let's try it for tangent. So again, we're going to need f prime here. So that's going to be secant squared of x. So if we apply our formula for the derivative of the inverse of tangent, we get 1 over f prime of f inverse of x. So that means we're going to get 1 over secant squared of inverse tangent of x. So if I draw my triangle with my random theta, tangent is opposite over adjacent, so this is like x over 1, right? So then if I do Pythagorean theorem, I get the square root of x plus 1, the square root of x squared plus 1 there on that hypotenuse. So now I'm trying to find 1 over secant squared theta, and I'm going to write it like this. So now what's the secant value of that theta? Well, secant's the reciprocal of cosine, which is adjacent, so we're doing hypotenuse over adjacent, so it's 1 over hypotenuse over adjacent, and then we're squaring that thing. So 1 over hypotenuse is root x squared plus 1 over adjacent, which is 1, and then we're squaring, so we get 1 over x squared plus 1. That is going to be our derivative of inverse tangent. Again, notice our pattern still holds. This is not a cofunction, therefore its derivative is positive. Okay, let's formalize in a rule. So first of all, of course, we're going to now consider chain rule as well. So when I do arc sine, that was 1 over the square root of 1 minus x squared. But I'm going to put u because that means when we write u here and we have dx, we're implying that that's some function of x in there. So then it's going to be times u prime. And some people may even write the u prime in the numerator because you can multiply the 1 times the u prime. All right, so that would be our derivative for inverse sine. Let's look at the other ones. I'm just going to give you a list. Sweet. The Wi-Fi here at the school is not working, it seems like. So hopefully it's working at your house and you can look up